So between the last video and this video, I made a few minor changes. Nothing crazy, don't worry. I cached out the primary shapes right here so that we don't have to do this poly reduce every single time and worry about the trace node and all that. We just cache out our results so that we have the primary section and the in-between areas. That's one thing I did. I also cached out these rocks because I don't want to go through all of this every single time either. So we just have our rocks. Whoops. They're right there. And last but not least, I also added this null, which signifies the beginning of our loop. And speaking of loops, that's what's coming next here. We need to have this Boolean process occur for each one of our pieces. So let's use a for each named primitive. And this will go through each piece, boolean out the edges, and give us really cool results. Okay, so we're taking this whole darn thing and putting a for each loop on it. And if we go towards the top, notice how I've still isolated just one piece right here for now. And I have the divide, and then we begin hitting the loop right here. Let's move this over a little bit too. It's just kind of bugging me. There we go. All right, so we can do this, and if we go through the for each loop, it will go through each individual piece and calculate things out. So what happens if we, first of all, use an assemble SOP to give us a name, and we bring back all of our pieces? So I turn off that blast, we now have all the pieces, and we're going through each one to Boolean. Let's see what happens. Well, what you'll notice is that if we take a look at this CPU right here, the CPU hovers anywhere from about 17% up to almost 50% the entire time. So no matter what task it's doing down here, we're not really ever using our full CPU to complete the task of booleaning out each one of these pieces. And that's because for each loops that are orange like that are considered to be a single-threaded process. In other words, they don't use your full CPU. And for most situations, that's a good thing, because in order for you to use your full CPU, you need to use a compiled block. So these yellow-looking things right here. And the compiled block will use your full CPU with anything that lives inside of that. But it comes with a catch. There are some side effects by using this compiled block. And sure enough, if we go down here, refresh this, look at that, we have some errors. For one, we don't have a supporting node type. So that tells us that the compile block is very picky about which nodes you're allowed to use and which ones you're not. So right now it does not like this attribute transfer. It's not supported by a compile block. So we'll have to figure out something for that section right there. If I go ahead and create a point wrangle, that's not the only problem. So let's say that just for a minute we bypass this whole thing, we ignore it, and we try refreshing this. It's also going to give us some errors with the transform because we're using some sort of expression that it doesn't like when we are centering our pivots right here. So in other words, these compile blocks are sweet, but the problem is that some things aren't going to be compatible. So let's start off by finding an alternate route for setting these normals to face the proper direction. Last time we used attribute transfer, we can't use it now. So instead, we need to rely on vex to find the nearest point, read its normal, and then apply it to the scattered points. Okay, and so we want to find the nearest normal and use that value. Start off by getting rid of all these loops real quick. I'm just going to hold down Y and cut everything off, put it to the side. And for now, let's just live without the for loops as we figure this out. Okay, so let's be sure that we're isolating the piece that we want. In this case, it's that guy right there. All right, down at this point wrangle, I know that I want to read an attribute from this stream right here. This stream has the geometry, and along with that geometry, the normal that we need to read from, right? So whenever we're reading points in Vex, we're going to use the point function. If I hover over this, press F1, we can see what ingredients we need. So we need to first of all talk about the geometry stream. We want to read from this second input, so that's index number 1. So that's the geometry. Attribute name is a string right here, and that's going to be called normal. And then, last but not least, the point number. And that point number has to correlate with a point number over here. And that will tell the points function where to go read the attribute. So right now we actually don't have that. And we don't have that because we don't know, visually speaking, like let's say I draw this out visually. Let's say there's a point right here. We don't know where that point should read an attribute from. So let's try to find the nearest points. Let's say it's right there. And use that ID to tell this point what its normal should be. Okay, that's how I'm picturing this in my head. So we have a function here called near points, and that will return the ID of the nearest points, or the point ID. So if we press F1, this needs to be an integer. So we'll say int nearest points, like that, is equal to this function. We need to look at geometry stream number 1. So that's the second input right here. And then PT is going to be at P for position. And I know that because if we go down here, PT says the position in space to find the closest point on the geometry to. So in other words, look at our current position, go to geometry stream number 1, return the nearest point. So there's a point function. Now we have what we need, nearest points. And this is going to be our new normal. So vector v at n, and let's see what that just did. There's our scattered points. Boom. There's the normals. And for the most part, they're all facing in the correct direction, which is good. In the next video, let's continue on by troubleshooting these for loops.